Welcome to Tollefson Physics. So what we're going to do today is we're going to talk about Newton's third law. And so Newton's third law is every reaction there's an equal and opposite reaction. And that's something we've always heard, but what does it actually mean, right? So what it actually means, as we've covered before, a force is a push and a pull. It's between two objects. And so what Newton's third law tells us is the force of one object is the same as the force on the other object pushing back. So if my finger is pushing with a certain force, say against this tape dispenser, the tape dispenser is pushing back with the exact same force. So a force always takes two objects, and the force between those two objects is always the same because they're both pushing on each other, or they could be pulling, but either way the force is the same between two of them. So let's look at an example of having let's say two blocks sitting on top of each other. So I'll make this kind of large. Let's say we got a 10 kilogram block, and let's make it a bigger block on top, a 20 kilogram block. And so I'm going to go ahead and draw force diagrams, quantitative force diagrams for each of these blocks. So I'm going to do the top block first. Yeah, we'll do it that way. And so the top block has a force due to gravity. It's on the 20 kilogram block, and it's by the entire Earth. And then, if I draw a dotted line around it, the only thing touching it is the 10 kilogram block. And so I'm going to claim that to be a normal force. But what's more important is it's on the 20 kilogram block by the 10 kilogram block. And that'll come in important in a moment. All right. And then I'm going to draw a force diagram for the 10 kilogram. And then I'm going to connect the two force diagrams using Newton's third law. And so for the bottom force diagram, I'm going to draw, and I'll try to make it about half that size. I have a force due to gravity on the 10 kilogram block by Earth, because I'm calling it the force due to gravity. But that's not the only thing that's pushing it down. The 20 kilogram block is also pushing it down. And so I'm going to add another one. And since I called it a normal force up there, I'm going to call it a normal force down here too. So this is on the 10 kilogram by the 20 kilogram block. All right, and then what's pushing up on it to prevent it from accelerating? And so I have the table. Yeah, we'll call it a table. So I have a normal force on the 10 kilogram block by the table. It's sitting on a table, let's say. Table. All right, and those are my two force diagrams. Now I can actually calculate what the force due to gravity is for both of those. So remember, the force due to that's not an F. The force due to gravity equals its mass in kilograms times g. And so for this purpose, we're going to use 10 for our acceleration due to gravity. So for the top block, force due to gravity equals a mass of 20 kilograms times 10 newtons per kilogram. And so that for the top block equals 200 newtons. And if I do the same thing for the bottom block, equals 10 kilograms times 10 newtons per kilogram, that equals 100 newtons. All right, so let me change color so we can start adding numbers to our diagram. So right here, I just said the force due to gravity equals 200 newtons. And down here, I didn't leave myself much room, but Fg equals 100 newtons. All right, so I have both of those. Now, on the top force diagram, I know that it's not moving, so the up arrow must equal the down arrow. And if the down arrow is 200 newtons, well, then the up arrow, and I'll write it over here, also must be 200 newtons. All right, that's because of Newton's first law. All right, so don't confuse Newton's first law with the third law. So essentially, the first law is telling me that if something is not moving, it's at a constant velocity of 0, then it must have balanced forces. And so I have balanced forces. Now, What if I look down here? I have this normal force. Normal force on the 20 kilogram block by the 10 kilogram block. Well, since they're touching, I better have something that sounds really similar to that, and I'm circling it in red. So I have the normal force down here on the 10 kilogram block by the 20 kilogram block. These two are related to each other because those are the two blocks that are touching each other. So if the top block has a normal force that it's exerting on the bottom block of 200 newtons, then down here, and I don't have a lot of room, I think I'll write it here, this down arrow must be 200 newtons because this equals this. That's my Newton third law pair. And what does that do for me? Well, now I know that the normal force, how much the table has to hold stuff up, that has to be 300 newtons because I have 100 newtons force due to gravity, and I have 200 newtons because of the pushing force by the other block. All right, and so this is how I can actually use Newton's third law to see what's going on. So one thing to think about when you're thinking about Newton's third law is don't worry about the size of something. Something that's bigger doesn't have more force on something that is smaller. And the example I like to use is when you're driving down the road and that little bitty fly smacks into your windshield. The little bitty fly is dead, right? You've got to clean it off your windshield a little bit later. But that little bitty fly exerted the exact same force on the windshield that the windshield exerted on the little bitty fly. Now what's the difference? The little bitty fly couldn't handle that force. It's dead. So don't confuse that with Newton's third law. The force is still the same between the fly and the windshield. The windshield did not exert a greater force. It just can handle a bigger force. The fly couldn't, right? So that actually comes down to mass, which is something else that we'll talk about.